factor is typically lower than 1, typically, because the wave height usually multiplied times 1.6 is, so DLT is higher than DG, and therefore this factor is lower than 1, typically. And therefore you get a B value that is comprised between 0 and 1. Okay, and here this final consideration is what I basically mentioned, so preliminary interpretation of the processes and direct experimentation, and etc. And I think for the drawings we are, or let's say for the design of drawings we are done. What instead I would like to discuss as the main topic of today is the stability of the units. And you already had some overview of this. If I'm not wrong, you studied the stability of units forming breakwaters through the Hudson formula. Am I correct? And Professor Archetti didn't discuss with you the stability of breakwaters, of units, boulders forming breakwaters. Did you study it? No? Okay, in any case, it doesn't make a big difference because probably she, after we talked about it, she decided to drop it because she knew that I'm talking about it. And this is an important issue. Like you form breakwaters, you build breakwaters or drawings, and the rubble mound structures are made by concrete or stone units. Concrete or stone because you need heavy material. Sometimes I had notice of breakwaters or drawings also made by other type of materials like metals. And typically they were materials that were recovered recycled by other uses. Actually, metal is a bit concerning for the corrosion and also for the environmental impact because the visual is not very good, of course. If you build a breakwater with units, with armor units, or even better, with stones, the visual impact is one thing. The visual impact is much worse if you use other materials like cars, recycled cars. It's possible. You can recover pieces of cars and bring and build a breakwater or a drawing by using recycled material. But you know, this was used in some cases, but especially when there is an emergency or there is a need to resolve a situation by minimizing the cost. But it's not, I would say that it's very rarely used today. You may see some kind of intervention like this. They are also a bit dangerous for the swimmers, but they are very rare. It's in 99% of the cases, breakwaters and drawings, they are made by units, armor or stone units. In this case, this picture shows you armor units taking the shape of tripods. What is the reason for giving that shape? That they lock each other and increase the stability. While if you use a circular shape, of course the stability is inferior. But the relevant question is to study the stability of these units, especially if the sides are sloped, and this is an issue that we need to carefully consider. So how can we do that? Usually the problem, as it is often done in coastal engineering, is studied through empirical approaches. So and I would say that essentially all the approaches that we can use are empirical. One of these empirical approaches is the formula that I mentioned to you just before, the Hudson formula. We will see it in a few minutes. What I would like to do is, before discussing empirical approaches, I would like to at least discuss the conceptual basis of a physically based approach to the study of the stability. You are used in other subjects to study the stability of hill slopes, the stability of structures by using physically based models. And let's try to use this approach here as well. It's more complicated because the drivers, the forces are less defined, there is more uncertainty in the study of the wave forcing, etc. But let's try to make it. And you know, this is extremely important because it happens quite frequently that you build breakwaters, groins, and an extreme storm comes and they are destroyed. Usually it's not a huge problem, but still it's, to recover them it's costly, so it's better if we make a proper assessment of stability. Okay, let's talk about the physics of it. And in order to talk about the physics of it, we can start the sheets method. First of all, here there is a link. I refer to text by Van Rijn of 2016. If you click here, you get it, which is much more detailed. Stability design of coastal structures, sea dikes, revetments, breakwater, and groins. And this is much more detailed. You don't need to look at it. I just wanted to show it to you, but you don't need, it's clear. Anyway, this text made by Leo Van Rijn, they are clear. I think they are really well done. I found a lot of inspiration in it. But again, you don't need to read it. And here it's a picture that I think is also reported in the text by Van Rijn, but I remade it. Let me see. Okay. Okay, let's study the stability from a physical point of view. And let's suppose that we have a structure with a slope beta. Beta is the angle between the horizontal and the side of the structure, as you can see there. And let's suppose that the structure is made by boulders, but this is not very important. But let's focus on an isolated boulder. I know that usually boulders are not isolated, but let's suppose that it's isolated now on the side of the structure. And then we have waves coming up. And let's suppose that the direction of waves is such that it's perpendicular to the longitudinal direction of this structure. So the wave is coming and climbing up along the side, like you see the arrow, the left arrow on the side. It exemplifies the forcing of waves. So let's study the stability of that unit, which has its own weight. And the weight is indicated here, has the multiplier of a coefficient C1, which is a shape coefficient of the unit. Because C1, it's a proportionality coefficient that multiplies a characteristic dimension of the unit, which is d, to the power of 3. Why the power of 3? Because you know that if you identify for a unit a significant dimension, a characteristic dimension, if you suppose that it's a cube, d is the side of the cube, and you know that the cube is the volume of the cube. So we want to express the volume of the unit. And even if it's circular, you know that the characteristic dimension is the diameter, and the volume of the sphere is proportional to the cube of the diameter. So this is why we express the weight has a function of the characteristic dimension cubed through a shape coefficient C1. And then there is the specific weight. So the product of C1 times the cube is the volume of the unit. And then we multiply the volume by the specific weight to get the final weight of the unit. And the specific weight, we assume it as immersed weight. So we have the specific weight gamma s of the unit minus the specific weight gamma of the seawater. It's immersed weight. You all know that when a body is immersed in water, the specific weight is reduced. It's reduced by subtracting by its own specific weight, the specific weight of the fluid where the unit, the body is immersed. This is Archimedes' principle. Okay? And this explains why both can float, can navigate, and don't sink unless they get fed by water. Okay, this is the specific weight which goes along the vertical direction. And then we are interested in the component which is perpendicular to the side of the structure, which is gamma cos beta. Beta, if you make an analysis of these angles, let's make it here. Beta is precisely, cos beta is precisely the multiplier that we need for W to get the component that is perpendicular to the side. So this is our structure. This is beta. And if we look at the weight component, this is W, and we need to get this component here. Okay? And so in order to get this component, we have to multiply W by the cos of beta, and beta is this angle here. Okay? Because this is 90 minus beta, and therefore this is again beta. Beta. Okay? So basically this component we can call it, there is no symbol there, but let's call it W perpendicular. W perpendicular is equal to W cos beta, while W, this component here, which is WS, let's call it WS, is W sin beta, which is indicated there. And this is a destabilizing force, destabilizing. Basically, WB is a stabilizing force. Why stabilizing? Because you know that if you multiply the perpendicular component to the side of the wave times the friction factor, you get a stabilizing force, which increases with the increase of the weight, WB, of the component perpendicular to the side, and increases with the increase of the friction factor. We will see this in detail when we move forward. And then we have a destabilizing force, which is the component of the weight that is parallel to the side. Okay, good. Now, let's suppose that waves come along this direction. So let's assume here, just for the sake of this computation, that this is a stabilizing force, the force of the waves, because waves typically they run up along the side. It's true that then the water comes back. It doesn't change anything to this demonstration, this conceptual representation. We can change the sign of this force. It's not really important. Now let's assume that it's a stabilizing force, so it's opposing the weight along the parallel direction of the side. Okay, so how can we compute this force exerted by waves? As you can see there, we can express it depending on the area of the unit that is exposed to the wave, the area of the face that is exposed to the wave. In order to estimate this area, let's assume that it's proportional to the square of the characteristic size d. An area is a square of a characteristic size, times another coefficient C2. C2, in this case, is the combination, or let's say that C2 is, for now, accounting for the shape. So C2 is also shape coefficient. And we will see later that it also accounts for some more.
But why C1 and C2 are different?
Because C1 is the shape that gives to you, is the shape coefficient that gives to you the volume, is related to the volume. And the C2 is related to the area of the exposed face. So they need to be different, because one is a coefficient expressing the area, and the other is a coefficient expressing the volume. So they need to be different. There is also to say that because if you take a perfect cube, of course they are identical, they are one, okay? But if the shape is complicated, in order to get the exposed area, the coefficient that you adopt to get the exposed area is different with respect to the coefficient that you adopt to compute the volume. Because keep in mind, for instance, a unit can be elongated along the side. So it can have a characteristic size that is representative basically of the 3 dimensions, that is relevant because it is elongated, but the exposed surface to the waves is very small. And therefore, this is why you need a shape coefficient that is different for the area. And also in this case, there is to say that everything is multiplied by the friction force. The friction force that is exerted by the fluid over the side. And C2 also takes into account that it's also a multiplier of that takes into account the irregularity that shape can cause to the friction force. Because, of course, one thing is if the friction force is exerted against a regular shape, and one other thing is if the shape is very regular. So basically, this is overall a shape factor, but it doesn't take into account only it doesn't take only into account the geometrical properties of the unit. It also takes into account the friction properties of the units. Because for the same friction force, which is related to the fluid movement, and the same geometrical shape of the unit, you may have a situation where the unit is less resistant. The friction, basically the resistance of the unit is reduced. For instance, because the friction between the unit itself and the side is different. And therefore this coefficient is called overall a friction coefficient, not merely a shape coefficient. So C2 is called, technically it's called friction coefficient. C1 is called shape coefficient. Because it takes into account also of the behavior of the unit against friction. This is probably the best explanation.
Professor, I have a question about the weight that the weight is divided into 2 components, but I didn't understand which one is stabilizing and which one is causing the...
Okay, in this case you have the component that is perpendicular to the side, which is stabilizing. We will see, and let me see if it is...
Because you call it WS.
It's called here... No, WS here. No, sorry, it's WP, perpendicular.
So WS
WS is side, along the side.
Ah, okay. I thought that S stands for
No,
stabilizing.
no, sorry. Sorry for that. These were symbols that I decided just here. And it means along the side. Okay? Okay, perfect. And so, let's study the critical equilibrium. And let me go back. The critical equilibrium is reached when these stabilizing and destabilizing forces are in equilibrium. So what is the stabilizing force? It's the component of the weight that is perpendicular to the side, and another stabilizing force is the friction force by waves. The destabilizing force is the component of the weight that is parallel to the side. Let's go back to here. So, basically, let's write the equilibrium between these forces. So, we have the friction force. I'm rewriting what is written here, but you know, this is in HTML. Let me write in the blackboard. Okay, so we have the force exerted by weight. I read on the figure C2 tau d squared. Okay, minus W sem beta, which is the component along the side. This is the difference between the components along the side, wave, action, and weight of the unit. The critical situation is reached when the component of the weight perpendicular to the side, W cos beta, multiplied by the friction factor, tangent phi, where phi is the friction angle, which you defined in other subjects, and you know that the friction factor is computed by multiplying by taking the tangent of the friction angle. When you are in equilibrium, these two forces are equal. Critical equilibrium. Okay? Stabilizing force minus the stabilizing force, which is equated to this, further the stabilizing force.
When we multiply a force by friction, what do we get also the force?
Sorry, say again.
If we multiply a force by friction,
This is a force
times friction.
times friction.
Friction is unitless.
Unitless, yeah. Okay, it's a tangent of an angle, so it's unitless. Okay. Just let me see, because I made okay. Okay, perfect. Okay, let's move forward, and then let's write this relationship here. Let's get an explicit representation for tau at the equilibrium by basically computing tau from here, and given that this refers to an equilibrium situation, which is critical equilibrium, we are close to instability, let's call it tau C, critical tau. So critical tau is equal to W, I'm just substituting here, W cos beta times tangent phi minus W sin beta divided, plus W sin beta divided by C2 d squared. now we can easily get to, sorry, I'm missing C1. Where did I use C1?
No.
Sorry?
No.
Yeah. Okay, in W. This was, so it's missing already also here. Yeah, it's missing also the where we correct. There was a C1. Is this true? No, it's in W, sorry, it's there. It's there. It's inside. It's inside. Because W is basically given by C1 gamma S minus gamma times dq. Yeah, sorry for that. Now we can substitute here then. So let's write Tc, tau c, is equal to C1 gamma S minus gamma d cube cos beta, okay, times tan phi, okay, and plus W sen beta divided by C2 d squared, okay?
So we express W just once.
I substituted here. Yeah, correct. Correct. I forgot. It is to be substituted here as well. Okay. So I don't have.
Multiply both with parentheses.
Yeah. Let me do it like this. We can put a parenthesis here, and then we can. Is it correct?
Yes.
Yeah. Okay, very good. And then we can do like this. Okay, and then we can write Tc, tau c, sorry, is equal to, okay, let me see, here we can take the common factor cos beta, this is what is done here, no, it's taken at cos beta, perfect. Okay, let me just rewrite it in this form, C1, I'm making additional steps with respect to what is done there in order to clarify the different steps that I'm taking. Gamma S minus gamma d cube, and then I can take cos beta, a common factor, which multiplies tan phi plus tan beta. I think it should be okay, yes, divided by C2. We are almost there. Let me see. So we are basically at the step that we see up there. This one. We are here. We got this, which you can see here. It's written in a slightly different way, but it's the same. Okay? And now, let's suppose that, from here, let's make an assumption that is not very meaningful in our case. Let's suppose that beta is 0. And let's indicate with C the ratio between C1 and C2. So if you suppose that the side is horizontal, which is not meaningful in our case, but it's meaningful in other cases, like when we study sediment transport in rivers, we use the same criteria. And the rivers the slope is very limited, and we assume that is 0. And in this case, just in order to get a reference for this simple case, in which the side is very, very, let's say, close to horizontal, then we can write, if again beta is 0, that tau c is equal to the product of c tangent phi times gamma s minus gamma times d, which can be written in this way. So, what can you see here? And of course, if you take a beta different from 0, you get a slightly different formulation, where you have also the value of beta included here. But basically, what can you see from here? You can see that the ratio between the friction force, which depends on wave forcing, divided by the specific immersed weight of the unit, multiplied by a characteristic dimension d. This is an adimensional number. This is a dimensional number, which is called Schill's number. It's a dimensionless number, which is called again Schill's number. This is constant. This is what this criteria tells you. And a very similar relationship can be written if beta is different from 0. Of course, you have a coefficient here, but basically the concept is that this dimensionless number is constant. What does it mean, this? It means that if we have the opportunity of estimating this constant, if you have this opportunity, by knowing the friction exerted by waves, this friction can become negative if you consider that the wave is not climbing up, but it's coming down. So if you want to make the wave destabilizing instead of stabilizing, you just have to change the value of tau c. Basically, again, if you know the friction operated by waves, you get an estimate of the characteristic dimension. So what is saying this criteria is that to estimate the characteristic dimension, you can estimate the friction operated by waves, you can estimate the constant there in some way, we will see how, and then you get an estimate of the characteristic unit. Okay? Okay, now, let me see if now there is to say that this is, computation is simplified. It's simplified because, we also assume, among the other things, that this, the friction parameter and also the friction factor, they are independent, they are constant, they are independent of the local situation. And basically, this is not true, actually. It depends on the wave forcing, also the friction parameter and the friction forcing, they depend on the wave forcing. So this is a simplification, but still it gives you an idea. One last thing before we break, actually I did one thing that was not completely correct. We cannot put a negative value of tau c there, okay? Because otherwise the whole relationship is not cannot be computed in the same way as before. We can, of course, start from the beginning and we can put a wave forcing on the opposite direction, but then the development of the relationship, we have to change some signs in the computation, and we get to a final relationship that is very similar, but we cannot get to it by simply changing here the sign. We have to change, we have to keep the friction positive and change the sign before than that in our computation. But from a conceptual point of view, I hope you understand the key message. The key message is when we make an equilibrium between stabilizing and destabilizing forcings, we get to a relationship where, which says that this dimensionless number, which is representing the equilibrium of stabilizing and destabilizing forcings, depending on the characteristic shape of the unit, is constant. Actually, it's not. We will see after in the continuation of our lecture that it's not because there are assumptions here. And in particular, the most evident assumptions that fail is that C2 is kept constant and the friction angle phi is assumed to be constant, which is not, it's not reliable, because the friction angle is going to change if you change your wave forcing, basically. If you remember how the friction angle is computed, it's computed on a dry material. When you get water running up and down, the friction angle changes, because the material gets wet, and depending on the wave forcing, the friction angle changes. So this is basically something that we need to adjust, and the way we adjust it is through empirical relationships. I hope it's clear. Let's take a coffee and let's meet again in 10 minutes.